Quickly review what we did. We did the following. Basically, this picture. If U is harmonic, then whatever the boundary value is, then the boundary never, the inside solution never go beyond this hyperplane. So that's you can basically cut the picture. Another thing is this basically the maximum principle, which morally you should think about this as a comparison theorem. Is you compare the solution with a particular one, which is the constant solution. If on the boundaries this all equals to a constant, then inside the orbit this all equals to the same constant. And equivalently it equals means that you can compare two solutions. So then we also look at the situation of right hand side. Then more or less you see this picture. Whatever you see on the boundary of the domain, then you see things like that. Then inside, you can build a kind of a hat. This hat is 1/2 to the n f area infinity norm 1 minus x squared. And of course, you can also build it below. Is whatever that happens. So. I basically compare with two of them. Then the U is less or equals to super phi plus 1/2 to the n 1 minus x squared f's area infinity norm. So more or less you see this picture. More importantly, or like a zero statement. Let me say. Zero, all the ground regularity, which is the following. If Laplacian equals 0 in ball 1, then we saw that U of x gradient of this less or equals to C0 like 1 minus x. Use area infinity form. And it's more interesting to look at the picture. It's let me take that equals to 1. So what do you see is actually a wonderful picture. You see the boundary phi maybe random. It's like any function between -1 and 1. The inside what we did is like inside the solution will interpolate. Each value of the U will be an interpolation of the value of phi. Actually, you can write it precisely. You can write it by the Poisson kernel. What's that? It's x minus y to the n. There's a constant phi of y. This is precise formula. So morally, what you think is that if I provide precise formula, of course you can get whatever you want. But the estimate is actually other way around. Is what the estimate says that is even you take this field like random functions. What this estimate says, I build up a lot of cones. For example, at the origin, I build up a cone. This cone is grow above the solution, and this angle is a theta. The tangent theta is controlled by this number. Then I not only build up a cone at origin, I build up a lot of cones. It's a little bit near to the boundary, the cone is a little bit sharper. then nearby, even up to the boundary, I did it. It's very, very sharp. And that is the picture of this estimate. And if you compare with mathematics and physics, you think about the following way. I mean, I think this way. So the physics is, of course, this equation is physics, right? And each of ux is, of course, that's physics. But each of ux is a physical observation. It is every day you go ahead and measure the temperature distribution. You see different u of x. But what's the physical law? Is this a physical law? And this is very, very precise. Same thing as here. It's very precise physical law. And this C0, this constant, is also a physical law, but not very precise. Right? And if C0 satisfies the conditions, then of course you can take C0 plus 1, say, satisfies everything what I said. Then you think about, I mean, why this is important? You know? I think is C0, and as well as all the proofs I will give to you, because C0 is kind of stable and nonlinear perturbations. So all those things is nice and precise, but the imprecise thing, which is C0, that give you a little bit of room. You can look at more general equations, more complicated equations, and they are really stable, and all kinds of perturbations. And in many cases, all like a nonlinear equation. You don't have this kind of formulas, but what turns out to be true is this kind of estimates. But nevertheless, you know, C0 itself is very valuable. That should be understood as a physical law also. So let me try to prove this ground regularity. So how do we prove it? Namely, this thing, right? I mean, if under the normalization condition, it is actually is what we did yesterday already. It gave a proof. I will try to give you maybe 2 proofs of this. Is this is lemma. I want to do this computation, but you know, I mean, I assume U is harmonic. Right? This is you basically you can close eye to make this kind of computation. So this bigger equals to 0. So this means that U squared is subharmonic. Actually, this also implies this, because if U is harmonic, gradient U is also harmonic. So you have 2 gradient U squared. Then, of course, you can compute this. Hygiene Choi did much sophisticated computation, but this you can do it like half sleep. Let me try to save time. I mean, everybody can do it actually. This would be bigger or equal 0 for actually any phi for lambda sufficiently large. Depends on phi. Let me this true for any phi. Choi did very smart pick, and here you can pick anything. For example, you can pick phi like what I did there, like 1 minus x squared. That will work, you know, like, or even many other things. Say, if you do that, I mean, it's clearly their question why you want to do that. But suppose you did it. This would be a subharmonic. So I have like phi gradient u squared, say at 0. Let me write it this way. Will be less or equals to his soup on the boundary. Right? This is because the subharmonic. I see that picture. Actually, I should say the subharmonic is also true, which I more or less did yesterday. So if you take this particular phi, this is bigger or equal to u squared 0 plus lambda u squared of 0. Then you can throw this away. And that's it. The thing is, this on the boundary, this phi, if you take things like that, this will be 0. This equals to c of u squared. This lambda is independent u. So that's kind of quick proof. You can do it like in 5. If you cannot do it in 5 minutes, you can do it in 10 minutes. I'm sure. It's quite algebraic. So this proof. Then you have all the things what I said. You might think this easy. Actually, this trick is called the Bernstein estimate. Is discovered by Bernstein. Basically 1900. Actually, if you look at the, I don't know, many of you heard about Ricci flows and all kinds of geometrical problems. The only computation of a Ricci flow that's successful, I won't say only. One of the fundamental steps is actually this guy. Is you look at the gradient estimate, one way or the other. So this computation, if you put it in a very complicated context, it can really drive you quite far. And the corollary of this would be that so I have origin gradient is bounded, so in half-ball gradient is bounded. If half-ball gradient is bounded, then in the half-ball I look at second-order derivative, it's also bounded, right? So I can have like gradient u squared less or equals to say c1 use L infinity, or I can say I can go as much as I want. It's like case order derivative. And I can also scale this one. It's gradient u squared 0 less or equals to c1 use L infinity ball 1 divided by r squared. And I can also understand this picture as it should be a parabola. If the boundary is like 1, then the second order derivative exactly grows like a parabola. And the third order case order derivative is r to the 2 to the k. R to the k is I have this kind of things. So next I want to really give you a proof of the Schauder regularity. So now it's too hot. Schauder, what I want to do is like Laplacian equals f. If this is holder, I want proof this is holder. So before I give you the proof, I hope you should first appreciate this is amazing statement. The way to appreciate this is this. What does it mean? This means that I give you a function, then you take a second order derivative, you get the Hessian, right? Then you take the trees. Then you found, suppose you give you f. Then f is holder means that the value of that, they are related, right? This holder continuity means the f is the value of it. It's kind of correlation. Then the conclusion is this is, by the way, this is sum of certain functions is very nicely or reasonably correlated, right? Now what's conclusion? The conclusion is each of those things in the sum, they are same kind of related, right? It's I say C alpha for the same alpha. How can you believe that? You know, it's like you say, I mean, two numbers add together, say less or equals 1. Then I say each number less or equals to 2. You say, no, I don't believe it. Right? It cannot be true, but it is true. So that's why it's so fundamental, and that's why it makes like all the mathematicians proud. It's very useful, and it's something almost like too good to be true. And the real reason behind it is actually the reason, the line above it is if it's harmonic, then all the derivative of u have qualitative control. That's the reason behind it. But nevertheless, we have to prove that. Then what's the difficulty? The difficulty really is here actually. The only information about this Hessian, you know, this say equals to, you say at the origin, right? Equals f0. The each of number you don't know. And the same as the understanding of this ground regularity is that you shouldn't try to find out what is this Hessian really is. The property of it is the physical thing, not each particular value. Let me come back to here is that you see this picture, right? Each value, say for example, what is u of 0? The estimate doesn't really say it. This is not very physical. U of 0 depends on experiment, depends on each daily life. If you perturb this boundary value a little bit, this thing will go with it. What is invariant is this constant. This cone always there. This cone is the physics, and this is observation. Same thing as here, as gradient u of 0. This guy is a globally defined vector. If you perturb this little bit, this thing will wobble with it. But what is invariant is this cone. Let's just go with it. You are not trying to find this guy, although you have to talk about it. But that's only the vehicle. Like I'm talking about this in English, right? In your mind, in many of your mind, it's Korean. That's fine, because the message is this picture, and this gradient u is only a vehicle to carry the message. So nevertheless, you want to prove the second order derivative is holder continuous. So you want to prove something is holder continuous. At least you have to roughly know what is d squared u 0. What is that? So let me repeat. Like all the arguments really have this non-linear character. Although what I'm doing is this is a linear one. So let me say the key lemma. Before I do that, let me say one thing. Actually, I did it like that formula is do. So let me just use that lemma. I say this fundamental step is that there is a R0 positive and epsilon 0 positive. This is for any alpha less than 1 bigger than 0. That depends only on this kind of things, maybe the dimension. So whenever this is true, with the condition that use area infinity bar 1 less or equals 1, which is f is almost like a 0, then there exists a second order harmonic polynomial. P of x, as I internally, I mean, let me write it down. Cx c, such that u minus p of x, L infinity ball r0, this all equals to r0 2 plus alpha. So although that's a clear, stated very clearly, let me try to draw you a picture and almost convince you that once I have that, I'm done. And then I will show you a proof that that's actually trivial. You can do it in 2 minutes. But the consequence of it is pretty deep. So first of all, what does it mean? It means the following: the real condition is actually here. This is the normalized condition. That is small, and that is the physics, and that is the conclusion, right? Let me draw a picture. What condition means? Condition means that u is less or equals 1, means that you see this, right? This is center, that is like 1, total like 2. Basically, u is this picture. U is in this cylinder. And also, you have a PDE. It's not all the u's. It's a function satisfies that. Then the conclusion says it's a little bit hard to draw like a higher dimension. Let me try to do a 2-dimensional one. This is my x. That is u. And first of all, I don't know the u something like that. Then add the PDE. Then implies the following. There's a universal R0, usually small. Then there's a second order polynomial. I mean, in higher dimension, you draw something like that. In 1 dimension, it has to be a straight line. And a second order polynomial of 1 dimension, it has to be a line. Then your solution u is very close to it. And this width, or double of it, is R0 2 plus alpha. Then what's the geometrical consequence is that your solution might might do something like that. Actually, near the boundary, you will see it's oscillating a lot. But when you go inside this little ball, all the solution has to be there, has to be squeezed, right? This I extracted a little bit, but in the middle I shrinked. And what it means that here and here is cleared. Solution cannot go there. So in the middle I squeezed the solution in very strong force, and the squeezing is R0 2 plus alpha order. Very, very strong. I squeezed. Then this kind of argument is clearly you can iterate. How you can iterate? This basically says that whenever you see this kind of box and plus this PDE, and of course with something reasonable, this f is almost like a 0. I mean even. Then the middle really very close to a polynomial. Then of course this mathematicians are really a group of really most liberal people. We see this as a box, right? But what is this? You can see, that's a box. I will make that into a perfect box later on, but it's really a box, right? I mean, a deformed box. And what it means after scaling and normalization, any box in the middle, I can squeeze it. This is what it says, right? The PDEs, you have to understand in all the possible scaling. The next thing what you do in a scale R0 squared, you can further squeeze it to another polynomial, and you squeeze it so much, it's almost like a second order polynomial in a smaller degree. If you do it infinitely many times, what do you see? You see an identical second order polynomial. End of the proof. Right? You are done. Okay? And that's the proof. But anyway, let me do the computation and to show you step by step. So geometrically, mathematically, physically, we are more or less done. So proof. So I start with this, right? U is L infinity less or equals 1. So I have this function. This will be y. This is u y. This is d sigma. That's less or equals 1. So this is harmonic. Right? Is this also less or equals 1? So H will be smooth. With estimate. So I can say anything I want. I can say first order derivative bounded, second order derivative bounded, third order derivative bounded. They all bounded. Very, very nice harmonic functions. So now I look at U minus H. Then what do you see? You almost look at the 0, right? The bounded value equals 0, F almost like 0. So you see that U of x minus H of x less or equals 1 over 2 to the n. I mean, this is very precise, but you don't have to worry about that much. This is as small as you want. So if U minus a harmonic function is as small as you want, then the harmonic function is smooth. So you can say U is very close to a harmonic polynomial. That's basically it, right? So of course, you can do it. So let the P of x be the Taylor polynomial, second order Taylor polynomial of H at 0. Of course, you have this. This P is less or equals to, they're like a C star x to the cube. But this universal constant is a gradient U to the cube L infinity by half, and maybe you want to divide by 6. But nevertheless, this is like a C3 over 6 x to the cube. This is true for all x less or equals half. So then you plug in. You get U of x minus P of x. I mean, this you triangle inequality. You get epsilon 0 C6 over 6 x to the cube, which is everything is really as expected, and you wanted it in the correct order. So what you do is less or equals to. Now you pick R0 small. Is actually here. If you pick that small, then this number you can make it less or equals half R0 2 plus alpha. That's the only place I used alpha is less than 1. This is if alpha less than 1 and R0 small. Nothing else. Of course, this cubical term. This may be 1,000. Then the cubical term, this is 2 plus alpha term. So that will be less or equals that. This is a free constant. I can just pick this to be half of R0 2 plus alpha. Then I'm done. I just let it to be. Now, I intentionally leave one detail, is that you might worry about this thing might be out of control. Actually, intuitively, it cannot. If you check the proof, the P, all the coefficient P would be universally bounded. Actually, this, by the picture, the P's gradient of P second order derivative cannot be unbounded anyway. So everything actually implied to be correct. But if you want to make sure, even this conclusion implies P has to have bounded coefficients. The thing is this, is that by triangle inequality, U is less or equals 1, right? The difference is bounded. So P's area infinity norm will be bounded. And P is a harmonic. So you use our gradient estimate of a harmonic function. Again, all the derivative of P has to be bounded. So that's is no problem. So if you want, let me say I start here. So I say P0 plus gradient P of 0 plus gradient P. I mean, that will be constant. I don't have to say anything. So that is automatically bounded. So now let me carry out the rest of the proof. Really show you that you can do it. Then let me do the philosophical discussion, because the estimate really means pretty deep and have really deep consequences. So what's the next step? Is proposition. Basically, this is the iteration. You better write it in this way. So f Laplacian equals to f in ball 1. I don't even want to write what's condition of that. I just say it's under the smallness and let me put a question mark, the smallness of f, which I will discover. And the normalization condition. Let me make sure I can start. Then there are harmonic polynomials. Pk of x equals to like a half of x transpose ak of x plus bk of x plus ck, such that u minus pk area infinity in this very R0 never change, is decays in the correct order. And I will fill in the gap as I move on. And at this time being, you don't really worry about it. So proof. And also and let me write one more thing. And this coefficient has the correct convergent property. So ak plus 1 minus ak less or equals c star r0 k alpha bk plus 1 minus bk. And the coefficient, they converge as they should. So the constant term converges really fast, and the first coefficient, the first order derivative converges, still geometrical converge, but with one less order. But after multiplied by x, they're exactly the same order. Second order derivative convergent like Holder fashion. This is C1 alpha fashion. this constant term is C2 alpha fraction, but you add together, they are the same. So proof. Of course, you say you take a P0 equals to 0. You don't have to do anything, and the P1 as in the lemma, and you don't have to do anything. I just provided it, and so you assume it is true for K. Suppose you did that, then you want to do it for K plus 1, and really this you can do it half sleep. What you do is you normalize it, right? You let me say bar x equals to u minus that, then you r0 k x divided by r0 k 2 plus alpha. You just do it what you should. Actually, in essence of this, you minus this, you make this line flat. Then you normalize x0 direction. You make that scale into 1. You make this into vertical scale into 1. So this changes this picture into this is 1 by 1 or 2 by 2. Right? That's exactly the normalization. Then once you have that normalization, you can apply the lemma again. Exactly what I'm erasing. Of course, you do one more computation. You do this equals to, you take Laplacian this. Laplacian that equals to 0. Laplacian that, you have a chain rule. You got R0 2k f of R0 k of x divided by R0 k 2 plus alpha f of R0 k of x. So you might see that goes to 0, but relax, don't worry about it. Keep going. So in the case, this thing is small. So smallness f s. Now you put it here. Is f's L infinity norm in ball R0 to the k is less or equals epsilon 0 R0 k alpha. That's exactly you discovered. Then you just put it there. If that is true, then you can iterate. This implies that you have a p of x less or equals to R0 2 plus alpha if x less or equals to R0. Right? I'm just exactly applying that. Then what is this? You put this formula to here. Then change the variable back, which is equivalent to say, then maybe you want to multiply that also. You get u of x minus pk of x is minus R0 2 plus alpha k of p. But here I switch the variable other way around. I get x over R0 to the k. That seems a little bit scary, but relax. I multiply that to here. I get one more power. Then this is the inductive step in front of you. If you define this, the whole thing, you define this as to be pk plus 1. Then you worry that there's the coefficient is converged as promised, and it does. For example, you look at constant term. This p is a second order polynomial of bounded by one harmonic function. So his value at the origin will be bounded by 1 actually. So this polynomial second order derivative is some number bounded by 1 times that, right? Of course, I mean, this, the difference from here to here is here, right? It's the difference. The difference from here to here is exactly this term. So the constant term is as that. Then let's look at the linear term. The linear term is you have x over r0 to the k. This coefficient seems huge. But here you have a k2 plus alpha. You lose 1, right? You get k1 plus alpha, exactly as I promised. The same thing as the second order derivative. You have everything should be at his place. Then you might worry about what does this mean, right? What does smallness mean? Actually, that's what is also supposed to be. That's forces f at the origin in any reasonable sense should be 0, right? And this, for example, morally, and you should understood in this way that if fx this all equals epsilon 0 x to the alpha, so everything can go through by shining colors, right? So it shows that if f at origin is 0 and the error is like that, then u is second order differentiable in this sense. Actually, this should be understood like a discrete second order differentiable. And philosophically, like what we did is really fundamentally strong, in the sense that this maximum principle, right, or f, is in terms of regularity theory, it's rather weak. Is from L infinity to L infinity. Now, this gives you like from C alpha to C alpha, from this very rough estimate, get the perfect one. So in one way of understanding it is in each of this discrete step, in each of this R0 to the K ball, we give an approximation of U by a polynomial, right? So each of the steps, this might be far away from the real thing. Even not far away, it's maybe very, very close. But they never be the real thing. So then what's going on is that in each step, you kind of lose the error, like 9% or 99%. Each step, you threw the error away a little bit. Then only through the limit, what you capture that, you can capture exactly what the second order derivative is. Right? So the limit is exact. And in each finite number of steps, you have some error. So this really is the power of infinity. So this, if you think about it, what we did is error divided by infinity equals to 0. Then at the end, we have a limit, and the limit is exactly U second order Taylor expansion. So it is clear. I won't really prove it. Is U P of K of X will converge, because all the coefficient will converge to because it's to a limiting harmonic polynomial with the correct speed is A infinity minus AK less or equals to R0 to the K alpha, then C star maybe tilde, etc. Then PK of P infinity U of X is L infinity ball R0 to the K will be less or equals to, if you put everything together, like C tilde R0 to plus alpha K. At least you can do that. But if this is true, in each of these consecutive balls, then you think this is your variable actually. If you think a little bit, this is same thing as to say you can just drop the dummy variable here. Maybe you have to change this constant a little bit. Mathematically, these two are really equivalent. If you think a little bit. So what that means is, through this infinite process, you captured the experiment, namely that the experiment of P infinity. So this depends on each physical situation, particularly for nonlinear equations. This is really hard to get. But the real important thing is this constant, not what that is. This depends on observation. That is the physical law. And the P infinity is exact. Okay, so should I stop here, or is an hour or 50 minutes? Yeah, I can talk 10 more minutes, or I still have 4 minutes. Let me okay. So this is fine, right? So now let me explain other loose ends. So how do you deal with this? How do you deal with this? Right? So that's actually very easy to handle. First of all, as it says, this f0 equals 0 is expected. So if you claim u can be approximated by a second order harmonic polynomial in this order, then the f has to be 0, otherwise it's inconsistent, right? But how do you make this true? It's trivial. So in general, because if f is wholly continuous, you do that, right? You do half of, say, f0 x1 squared, right? This will be f of x minus f0. Then you say this is my f1, which is 0. Done. The other thing is, how do you make sure fx equals to let's say epsilon 0, something like that? Why this? How can you make that small? For linear equation, it's very easy to do. For example, in this case, you just say, let me play dumb, just multiply. Right? In the case, say that let's say equals 1. Otherwise, I divide by f1 like a norm. That will be it, because epsilon 0 is really universal constant. So that handles the smallness. This is for linear equation. You can do this. You can also do a dilation. You get R0 f R0. So you can make this small as you want. So let me go back in the statement that I have two conditions. One is a normalization condition. This can be also handled as a u divided by his L infinity norm. There's another condition. Is this kind of smallness condition. This is called the smallness. It's also important. And in Friday, Haijun Choi will show you the regularity of Navier-Stokes equation. And for nonlinear equations, the smallness is not that easy to achieve. So it's typical thing about smallness condition, exactly like what we say in the implicit function theorem. If you look at the proof, it's exactly modeled by the implicit function theorem. Is we always have some kind of smallness condition. It's unavoidable. So for nonlinear equations, you better say I have smallness, then there's no way out. Then you look at your situation, when and where you have the smallness. Then that's usually where the partial regularity coming from. And for linear equation, you can always get it for free. For nonlinear equation, that's a kind of that's life. So you cannot change the smallness. So it's really modeled by the implicit function theorem. What you see is for the limiting equation, in the case the f equals 0, everything is nice. And this is the perturbation argument. If f have reasonable perturbations, then its regularity is perturbed in the correct way. And what you got is, at the end of the day, you capture quite nonlinear information about u, and it shows the error is as expected. So if I can go to an hour, I can use 10 more minutes, or that's about.
You can do whatever.
Okay, so let me show you another picture. Maybe I will do it, and I will explain more in the afternoon. So this is really nice. You can really see the estimate by naked eye. So let me give you another approach. It's more or less connected with what the Hatchin did. Is the following: is lemma is that a Laplacian u equals to f, u equals 0 on the boundary. Then a gradient u squared. This is f squared, and maybe there's a constant, which is very easy to prove. You just multiply equation by u, then integration by part. This is the typical energy estimate. But let me recall what we did for the maximum principle approach. Is that for maximum principle from u to area infinity to u's area infinity. This is from L2 to H1. But so what? It's also give you some kind of control. You should understand this as a really error estimate. If this equals to 0, you have a L2 perturbation. Then the solution to the 0 solution, which is you don't see, have this H1 error estimate. Picture, you have the same picture, right? So now you have the perturbation lemma. This is stated exactly same way. For an alpha less than 1 bigger than 0, there is a R0 less than 1 and epsilon 0 less than 1 bigger than 0. F Laplacian u equals f in ball 1. With this normalized condition, but normalized condition should be fit in this new physical phenomenon, which is that I assume this is true. This is normalized 1. Then also that I assume f is small. Then there is a px harmonic second order polynomial such that this is true. Gradient of u minus p squared average ball 1. Then I take square root. But this is scales like a u. That measures how big u is in the correct scale. This less or equals to R0 2 plus alpha. Again, the proof is exactly the same. So how do you do that? prove, of course, you let H be this. Then the H minimize the energy. So this is true. Right, this will be a constant. Then all the derivative for U would be bounded. I didn't say that, but it will be true. So now you have this equation with zero boundary condition. Then of course, what you have is gradient of U minus H squared for 1 less or equals to average. This is C0 F squared. But you understand this like almost like nothing. Then this is bigger or equals to, you shrink the ball, you can shrink it anywhere you want. Right? It's still small. Wherever this is almost nothing, the left hand side you can shrink anywhere you want. It's still nothing. But what do you observe when you shrink the ball? When you shrink the ball, this H becomes very close to a polynomial. Then you just write it down, you are done. So this means that ball 1, ball R0, you look at this P of square. I mean, I won't do it. I will do it. Okay, this is ball 1. You use a triangle inequality. H. And to make it precise, you might multiply by 2. But this is really tiny. It's epsilon 0 square. Then this is a smooth function, right? Smooth function is H minus the second order becomes cubic order. Cubic order take gradient second order square is fourth order. So you get C star ball R0 to the fourth. Then clearly you can make it less or equals to ball R0 to the R0 1 plus alpha, then doubled. And if you trace back, that's equivalent to what you wanted to prove. Then you see this picture. So the condition, you better think about the following way. This is H1, like semi-norm. Then the condition is ball 1 is 1 by 1. Then this implies in a smaller ball, you exactly see this kind of things. But the picture you see is H1 semi-norm. But mathematicians are liberal enough that they are the same. So in the afternoon, I will show you that it is indeed true that there's a theorem. There are actually a sequence of theorems proved by Caponado. It says that if you look at the Holder space, in any reasonable norm, at all points, all scales, they are all equivalent. And if you read that theorem, then re-examine what we did. In certain sense, it says that if you measure the function, not a semi-norm, if you measure the function by harmonic, by Laplacian, if that in certain way is Holder continuous, it says U is Holder continuous. That's exactly the Schroeder theory. Okay, so let me stop here.